All right, so we're going to do the rest of 14.6 here. So remember that from 14.6, from when we started it last class, we know how to do the derivative in the x direction and the y direction, but what we're looking for is a directional derivative. All right, so to find that, we are doing, and these were from last time, right? And so we have to find this vector here with our derivative with respect to x and the derivative with respect to y, and we're going to dot it with our unit vector. This unit vector is going in the direction that we want to do the derivative in. So you dot those two things. All right, so usually they give you a unit vector. So if they give you something from the unit circle, you know it's a unit vector because those lines are all 1 unit long in this direction right here. And then we had to find our fx and our fy. They told me a point, so I plugged those in and got these numbers. So in the end, it was just those two numbers dotted with my direction vector. And so this became my directional derivative. So this is my velocity in the direction when I'm going in the 30-degree direction. Okay. All right, so then we did another example here. We got another one. Then we named this guy. We named this fx, fy. We named it our gradient vector, and it was called del f, right? So down here, we just find del f, plug in 0, 1. So we did that last time. Then we came to, this is about where we stopped last time. So we have our definition of our directional derivative here, and it's a unit vector. And recall this formula where the cosine of the angle between two vectors is dot product over their magnitudes multiplied together. So if I move these magnitudes to the other side and multiply it over, we get this formula. So since I have a dot product here, and that's a dot product, we're going to like replace these names for u and v, and then also over here. So we did that here. Well, our magnitude of u is 1 because it's a unit vector, so we got rid of it because it's just 1, so we have this. So our directional derivative can be thought of as the magnitude of the gradient vector times the cosine of the angle, the angle between the unit vector and the gradient vector. Okay, so you don't usually know that angle, but if you do know it, you could use this. So think about this formula here for the directional derivative. It's kind of, this is not going to change right here, the magnitude. It changes based on the point that you're at because of the numbers you're going to plug into it, but it's like pretty stable. What's going to change is the cosine of the angle. So depending which direction you go, the cosine of that angle can be anywhere between 1 and -1, right? Because if you have a cosine graph, I don't want to draw it on here, but if you have a cosine graph, it goes up to 1, goes down to -1. So that's the highest and lowest it can go. All right, so then we came to here, where we started today. So basically, this is a fixed value, and it can change, based on the numbers you plugged into it. But this part right here, cosine is the largest, at 0, because cosine starts high, and then it goes low, and then it goes back high again, right? So when theta equals 0. And then it's at its low point at 180 degrees. So, cosine of 0 degrees is equal to 1, and cosine of 180 is equal to -1, right? And so when your angle is 180 degrees, or pi. All right, so basically what this is going to be telling you is when your gradient vector and your the direction you're going, when your gradient vector and your direction that you're trying to do the derivative in, when the angle between them is nothing. So when they go the same direction, that's the best possible scenario. So if you're going in the direction of your gradient vector, if that's the direction that u is already going in, then that is when you're going to get your maximum directional derivative, your maximum velocity. So that's what we're trying to get out of this. Okay, so the magnitude of your gradient right there is the maximum value of the directional derivative. In other words, it is the maximum rate of change of the gradient, that's an E, or the slope basically, where the velocity is the highest. Okay, this occurs when your u vector, the direction you're trying to go in, is the same direction as the gradient vector, which is del f. Okay, Right, so therefore the least rate of change occurs when we go the opposite direction. Okay, so for example, like if you drew pi over 4, the opposite of that would be this way, so that would be 180 degrees later, so 5 pi over 4. That's just like a little, trig facts or whatever. All right, so then we went and did some an example here. So I'll read through the example in a second, but let's do our fx and our fy because we know we will need those. So derivative with respect to x, the x goes away, so that's 1, and then e to the y. And with respect to y would be e to the y. X just hangs around. All right, and we are trying to do the rate of change at the point 2, 0, so let's plug in 2, 0. So if I plug in 2, 0, I get e to the 0, which is 1. 2 times e to the 0, so that's 2. So basically I have that my gradient vector at 2, 0 is the vector 1, 2. Okay, all right. So now I want to find the rate of change at this point when I go in this direction. So I have to go in the direction that goes from P to this point. So we're going to call that Q. So if I want to go from P to Q, I need a vector that goes from P to Q. So I take Q and I subtract P. So 1/2 minus 2 would be negative 1.5, so negative 1.5. And 2 minus 0 would be 2. Well, but remember, this is going to be my U vector, my direction. So I need it to be a unit vector. So you need to divide it by its own magnitude. So the square root of negative 1.5 squared plus 2 squared. All right, so when you do all that math right there, you end up getting negative 3/5 and 4/5. All right, so this is going to be my U vector. Okay, so I just need to dot these two things, do the dot product, and then I'll have my answer to part A. The rate of change, the velocity, the rate of change going from P to Q from that point. All right, so du of my function at 2, 0 going in this direction is 1, 2 dotted with negative 3/5 and 4/5. Okay, so you do all that right there, you get negative 3/5 plus 8/5, so you get 5/5, so you get a 1. Not exciting. All right, and then in part B. Part B says, in what direction does your function have the maximum rate of change? And what is this maximum rate of change? So it has the maximum rate of change in the direction of del f, right? And so in our case, in the direction of, at the point 2, 0, is this guy right here, right? So 1, 2. And what is that maximum rate of change? Well, you would do the magnitude of 1, 2, so you'd get the square root of 5. So that is the most that the velocity is going to be, and it goes in the direction of the gradient vector. Now, since this is a two-piece vector right there, so you have your x and a y. So imagine if you go over 1 and up 2, you can actually find the angle of that vector right there. I don't know if you remember from pre-calculus, but when you have a vector AB, the tangent of your angle is B over A, right? And so that's your opposite over your adjacent, so like 2 over 1, right? So it kind of makes sense in this picture too. So the tangent of this angle is 2 over 1, so you go in your calculator, find inverse tangent, and you get 63.4. Right. So in this case, we could actually find the direction, but if there was a third number, if it was 3 dimensions, we wouldn't be able to do this formula anymore, so we couldn't find it. So we would just make this statement: the maximum rate of change is in the direction of del f, of the gradient. Okay, and that's all you have to say. You can still find the magnitude. All right, so this last little bit, this is just an extra example I did here. I was doing my derivatives over on the side. I said, in which direction does the temperature increase the fastest at this point? So my derivative, I have to do a quotient rule. Derivative 80 is 0. That takes care of the first part, minus the derivative of the bottom with respect to x would be 2x times the top of 80, then the bottom squared. So the rest of the derivatives are basically the same. You're just changing this derivative, what you're doing respect to. So here you're doing the respect to y. so that would become 4y. The 0 is still in front here, so it's all there. Then at the bottom you have 6z. Sorry, they're changing classes, so it's really loud out there. All right. So anyway, you plug in all your numbers and you get these three values. So there is your gradient vector. All right, so there's your gradient vector. And if you wanted to find the maximum of this thing, the maximum of your velocity, so you do the magnitude of this gradient vector. So square each part, add it up, and there it comes out to about 4. All right, so and the reason it has a degree symbol there is because it's temperature, right? So it's 4 degrees Celsius, right? Yeah, Celsius per minute, or yeah, okay. All right, so anyway, let's see, meters, Celsius per meter, sorry. And so yeah, that was just like a little example, and this maximum rate of change is going to this maximum rate of increase basically is going to be in the same direction as, oops, I put the wrong triangle. Oh yeah, that's the right triangle. So del t. So you don't have to find the direction. You know, it's 3 parts right here. You don't have to find it. You just have to say that it's in that direction, and then you can do the magnitude to figure out what the maximum is. Okay. All right. So this last little piece right here, a tangent plane. Well, you can see from this picture here, your gradient vector, your del f, is normal all the time to your surface. So the direction of the gradient vector, it is perpendicular to the tangent plane. Okay, so that's great. So not only can I use it for the equation of the tangent plane, I can also use it for the equation of a normal line. So that gradient vector gets used for a lot. All right, so the equation of a plane looks like this. So that gradient vector right there, that's going to be my A, my B, and my C, right? And then we'll do the dot product and put D on the other side to find it like we've done before. Okay. All right, so you can we're gonna like just do this the old-fashioned way that we're always used to, but you can always also write it like this. The equation of the tangent plane is going to be del f dotted with x minus x0, y minus y0, and z minus z0 equal to 0. So remember, this thing right here, that is just your fx, your fy, and your fz dotted with that stuff right there. So we are going to find this, and then we are going to just basically do what we've done before. But if you follow this format here, you will get the same answer, but we're just going to kind of do what we've always done. So at first, we got to move this 1 over. So xy sine z equal, or minus 1 equals 0. So now I need fx, fy, and fz. Okay, so with respect to x, I get y sine z. With respect to y, I get x sine z. Oh, I can't write. And with respect to z, I leave the xy alone and I get cosine z. All right, so now we got to plug in these numbers. So plug in a 2, and sine of pi over 6 is 1/2, so it's 1. Plug in a 1, and sine is again 1/2. Plug in a 1 and a 2, so that's 2. Cosine is radical 3 over 2, so I get radical 3. All right, so that right there, that is my normal vector for my plane. So I'm going to use it. I'm going to put it in front of the xyz, so 1x plus 1/2 y plus radical 3z. And then remember that we dot this normal vector with my point to get my d value over here. Okay, so I get 1 plus 1, so I get 2 plus pi over 6 times radical 3. So pi over 6 radical 3. So that's just ugly. Okay. All right, so there is also the normal line to the surface at the point in question. So remember, this is a line perpendicular to the tangent plane, okay, and passing through the point being used. So the trick is you already know the direction of this line. Remember from the picture on the other side, a couple pages ago. All right, if you have the equation of the tangent plane, the direction of that plane is its normal vector. So you're going to take the normal vector and just write an equation of a line with that vector and that point. Okay, and so we're going to skip this example here and just do it, whoopsie, and just do it for this information up top here. Okay. All right, so remember the equation of a line looks like this: x equals at plus x0, y equals bt plus y0, z equals ct plus z0, right? So a parametric equation of this line with this normal vector and this point would be 1t, so t plus 1, right? The y would be 1/2 t plus 2. And my z would be radical 3t plus pi over 6. So that would be the equation of the line normal to the surface at this point. Okay, and then there's your homework problems down below, and I'll see you next time. Your homework tonight is to have these done, but also watch the video for, I'm going to do about 15 minutes of a video for 15-7. All right, bye-bye.